Welcome to the first in a series of aviation weather safety presentations. My name is Patrick Guide. I'm an FAA safety team representative in North Dakota and a National Weather Service Bismarck meteorologist. This first presentation is entitled Judging the Wind and deals with operations in high winds and turbulence. So why wind? Well, in a 2003 through 2007 study of Part 91 weather-related accidents, the overwhelming majority were wind. When we break down those wind-related accidents, we see that gusts, crosswinds, and tailwinds were the leading factors, and most of them occurred during landing, followed by takeoff. So why wind? Well, it is the number one weather-related aircraft accident factor, with the leading causes being gusts, crosswinds, and tailwinds. Most likely phase of flight is landing. Wind was also a leading factor amongst the weather-related accidents for Part 121 and 135 operations. While some amount of crosswinds and turbulence are unavoidable and a part of day-to-day flying, the majority of wind-related accidents are avoidable. Always obtain a weather briefing to recognize the wind-related hazards. Know your aircraft's wind thresholds and, more importantly, your own personal wind thresholds, and remain proficient. If you have not flown in winds in a while, seek some time with an instructor. Next, we'll go over some sources of wind information. Of course, we have the TAF and also the Tactical Decision Aid, or TDA, which is a color-coded graphical representation of the TAF, which also includes calculated crosswind components for the runways based upon the forecast winds from the TAF. And this is available on the National Weather Service Bismarck Aviation webpage, which is the North Dakota Aviation Weather Briefing page at this web address. We also have AirMet Tango, which is for moderate or greater turbulence, a reference to a single-engine aircraft, and outlook sustained surface winds of 30 knots or more, and low-level wind shear. It is updated every 3 hours with 3 hourly forecasts for the next 12 hours and provides a quick snapshot of possible high wind areas and or low-level turbulence along a route. Next, we'll go over some favored areas for winds across the northern plains. In North Dakota and across much of the northern plains and upper Midwest, we see our strongest winds behind a cold front on the backside of deep low pressure. So we have this low pressure system across southeast Ontario and high pressure across eastern Montana and down into Nebraska. The black lines are isobars, or lines of constant pressure, and the tighter these are, or the tighter they are packed together, the stronger the winds are. So we see a very tight pressure gradient on the backside of this low pressure system and behind this cold front. So where are our strongest winds on this surface analysis chart? Well, they're right where we expect them to be, right on this tight pressure gradient behind the cold front on the backside of the surface low. So what should you always think about when you're looking at this surface analysis chart in your pre-flight planning? Well, am I going to cross any fronts, which would be related to fuel considerations for headwinds and tailwinds? Is my destination airport near a front for possible wind shifts? Are there outflow boundaries or any squall lines that are actually highlighted on the surface analysis chart, which will represent a severe turbulence and low-level wind shear threat? Single-runway airports, very common across North Dakota and much of the United States in smaller towns and cities across our nation. While most runway configurations for these single-runway airports are designed to take advantage of the most common prevailing winds, high-impact weather events often yield non-climatological wind directions, and this presents the potential for significant crosswinds at these single-runway airports. So a lot of these smaller airports, single-runway airports, don't have any TAFs. So what we need to do, we need to check the surrounding TAFs across the area, the surface prog charts, the latest observations to determine the wind direction and the strength at your destination, arrival, and alternate airfields prior to and during flight. So for single-runway airports where crosswinds are likely, having an alternate airport with a more preferable runway configuration is essential. Federal regulations dictate that a fully extended windsock indicates a wind speed of 15 knots. If the windsock is flapping, gusty or fluctuating winds are occurring, which may lead to airspeed and flight control effectiveness changes on the final to flare. So if we have winds that are coming off this hill and possibly impacting the building, so the winds are coming out of the screen in this example, we could have some eddies that are forming along this building, and which would then propagate towards the windsock, causing it to flap around, and that would clue you into potentially some eddies forming that may be transported across the runway threshold and may lead to some airspeed fluctuations on the final to flare. Mechanical turbulence. We always want to gain knowledge from local airport personnel or other pilots regarding known mechanical turbulence hazards resulting from winds interacting with terrain or airport structures when they're flying into a new or unfamiliar airport. Overfly the field. Make note of the wind direction, possible structures, trees that may cause eddies to form in the final approach to touchdown zone. During run-up, we want to check the lift-off to initial climb zone for possible hazards that may generate low-level turbulence. Knowledge is power. Anticipating and planning for possible turbulence and airspeed fluctuations on short final or takeoff allows these operations to be conducted safely in windy conditions. Especially in regards to crop dusters, they are very susceptible to mechanical turbulence when operating near tree rows and or terrain. So before beginning operations, we want to make note of the wind direction from the crops in the field, trees, or if possible, if there is a weather observing station near the field that you're operating in. Want to think about what portions of the aerial application site are most likely to generate mechanical turbulence. Are there any eddies clearly evident? For example, dust devils in the fields or swirling leaves or grasses. And you want to use an application pattern that mitigates the risk. So in this mechanical turbulence example, say we have a headwind that's coming out of the screen, so it's rolling over the terrain and forming eddies interacting with the terrain and the trees, and these eddies are being transported into the initial climb-out zone. So by recognizing the terrain that is in the initial climb-out zone in the trees and the taking advantage, obviously, of a likely headwinds situation, we can anticipate some low-level turbulence and possible airspeed fluctuations in our initial climb-out. Wind speed correction on takeoff. When I hold the aileron into the crosswind, and this generates a downward force on the upwind wing, which counteracts the tendency for the crosswind to raise the wing. Want to use rudder to maintain center line, and as our airspeed increases and flight controls become more effective, our control pressure should be relaxed to combat the crosswinds. Always want to stay updated. If flying into a towered airport, ask for wind checks from the tower personnel while in the traffic pattern. If you're flying into a non-towered airport, take advantage of the co-pilot or passenger to monitor ASOS or AWOS on the secondary radio and provide you updates. And from this information, are the winds fluctuating? Are they steady? Is landing on the intended runway still feasible? Do I need to carry more power, use less flaps? Making those decisions well in advance before we begin our approach. When to go around and divert. If you're using a slide slip to counter crosswinds on approach to landing, and the required bank is such that full opposite rudder cannot prevent a turn, then the winds are too strong to make a safe landing. You want to initiate immediate go-around. Either make an approach on a runway that is more favorably aligned with the winds, or divert to an alternate airfield. Anticipate. If you're at full rudder deflection while in final approach, consider a go-around before reaching the runway. Decreasing airspeed during the flare will reduce the effectiveness of the control surfaces, and the controlled inputs that would be required to maintain the center line may exceed the ability of the aircraft. Final approach wind gust correction. The FAA approved correction to final approach airspeed is to add 1/2 of the gust factor to the normal final approach airspeed. So a quick and easy example, sustained winds are 25 knots with gusts of 35 knots. That gives us a gust factor of 10 knots, and thus we'd increase our final approach speed by 5 knots. But what is growing in popularity is the use of GPS ground speed to anticipate wind shear on final approach. Using this procedure, the pilot matches the GPS ground speed to the normal final approach airspeed. So for example, our normal approach airspeed is 80 knots. Our headwinds are 30 knots, which gives us a ground speed of 50 knots. If GSP ground speed was matched to the normal approach airspeed, GPS ground speed would be 80 knots and the airspeed would be 110 knots, given 30-knot headwind component before the wind shear encounter. Now we assume the worst-case scenario of a maximum wind shear resulting in a loss of 30 knots. So, for example, all the headwind is lost. The ground speed would remain at 80 knots due to the inertia of the aircraft overcoming the effects of the sudden wind shear. Minimum airspeed within the shear encounter would also be 80 knots, which is the indicated airspeed that is normally used on final. Touchdown ground speed determines the landing roll distance, not airspeed. Thus, carrying excess airspeed when crossing the runway threshold will not increase the landing distance required. However, carrying extra airspeed results in a lower nose attitude than normal when crossing the threshold. This can be countered in two ways. Enter a prolonged flare to dissipate the excess airspeed, or gently roll the mains on the runway and be aware that the nose gear may touch down at nearly the same time. Holding back pressure on the control wheel and braking gently during the initial rollout needs to be used to prevent wheelbarrowing. Once on the ground, don't let up. While the airplane is decelerating during the after-landing roll, more and more aileron is applied to keep the upwind wing from rising. Since the airplane is slowing down, there is less airflow around the ailerons and they become less effective. At the same time, the relative wind is becoming more of a crosswind and exerting a greater force on the upwind wing. When the airplane is coming to a stop, the aileron control must be fully held towards the wind. Most importantly is knowing your own personal thresholds for winds and crosswinds and turbulence, which may not be the same as your aircraft. What are your personal crosswind thresholds? What has or what would make you feel uncomfortable? Or has your instructor suggested any limits? When was the last time you operated in strong winds or made takeoffs and landings with significant crosswind components? Never be afraid to get a refresher from an instructor. Don't blow around. Stay on the ground.